Hello everyone. Thank you for providing me with this opportunity to present my research paper at the IEEE RCAR conference. My name is Mingda Zhu, and the rest of the co-authors are Tongtong Wang, Houxiang Zhang, and Guoyuan. We are with the Department of Ocean Operations and Civil Engineering at NTNU Aalesund. The title of the paper that I'm going to present is Ship Maneuvering Model Identification under Wind Disturbance. Here are the contents of the presentation, which are in line with my paper structure, and they are organized as introduction, related work, methodology, experiments and results, conclusion, and references. Let's begin with the introduction. The identification of the ship maneuvering model has always been an important task. The reasons are listed below. Firstly, there are more intelligent ships being built. Secondly, the target to move forward to ship automation has been outlined, and parameter identification can facilitate this process with the establishment of the ship's maneuvering model. Thirdly, commissioned vessels can also benefit from this process because it helps with the collaboration of the ship model with large modifications. Lastly, it will increase the efficiency of sea trials, providing more important assistance and reference. In order to determine the ship maneuvering model, the estimation of ship hydrodynamics coefficients is often essential. But there are some research challenges that we had to face. First, environmental disturbances. Environmental disturbances are often neglected, while the calm water condition is used instead. Second, measurement noise. In real life, the data is inevitably polluted by noise. Third, there are very limited examples where environmental factors are considered. Therefore, the aims of this paper is to estimate the hydrodynamic coefficients under wind disturbances and to study the effects of wind and the measurement noise. Let's move on to related work. System identification is a well-acknowledged approach and is now extensively studied for its low experimental time and cost. In this domain, least squares method is a very classic method and it's very sensitive to noise. Also, it leads to a long consistent estimate. As for artificial neural network, it's a popular method for modeling nonlinear systems. However, it's a black box which cannot reflect the physical properties of the ship. And support vector machine (SVM) can retrieve the ship model structure, and it utilizes finite samples of data and achieves a good performance. And then we come to the methodology. To address the uncertainty of identification under wind disturbances, an identification structure is proposed as shown in the figure. The flowchart consists of three major components: data generation phase, estimation phase, and validation phase. In the data generation phase, the data is obtained from the simulator and preprocessed, which is that later fed into the estimation phase. In the second phase, the SVM method is employed to identify the hydrodynamic coefficients of the ship maneuvering model under different wind conditions. Lastly, the identified hydrodynamic coefficients and the model performance are validated. And then we briefly discuss how to derive the identification model. We start with ship dynamic model under wind disturbances, as shown in the upper part of PowerPoint slides. On the left-hand side, these are the equations in surge, sway, and yaw motion. And on the right hand side, the wind force and moment, denoted as tau, is calculated as provided. And then we use a 3 degree of freedom Abkovitz model of a mariner class cargo vessel to express the forces S prime, Y prime, and M prime. These are the long-dimensional forces and moments. And S prime with subscript, Y prime with subscript, M prime with subscript are the hydrodynamic coefficients that we would like to identify. And by using velocity difference method, we can finally obtain the identification model as shown on the top. A, B, and C are long-dimensional hydrodynamic coefficients. S prime, Y prime, and M prime are input vectors which contain the information of velocity components and rudder angle. The SVM model using linear kernel for regression is also provided here, which can be used to identify the hydrodynamic coefficients from the above structure. And the noise model is also provided, utilizing a Gaussian process. And then we move on to experiments and results. The ship simulation experiments are performed using Marine System Simulator. And a sequential zigzag maneuver is used for data generation, including 40 degree, 40 degree, 20 degree, 20 degree, and 5 degree, 5 degree. And the rudder command of the sequential zigzag maneuver is provided in the figure. The wind speed is set from 1 meter per second to 12 meter per second with an interval of 1 meter per second. And the noise level ranges from 1% to 20% with an interval of 1%. The model performance evaluation is conducted using mean distance error, which is expressed here. N and E represent the original north and east position respectively, while N hat and E hat are the simulated north and east positions. 240 sets of hydrodynamic coefficients are identified. 4 turning tests from minus 10 degree to minus 40 degree, and 2 zigzag tests including 10 degree and 10 degree, and 30 degree are tested. The generalized NDE is also calculated. The generalized NDE is the mean value of the summation of the average value of NDE in turning and in zigzag. The contour plot of the generalized NDE is shown in the figure. As we can see, the contour plot can be divided into 4 regions according to the range of the error, and the value of generalized NDE increases as the wind speed and wind measurement noise become larger. Besides, region 1 takes up the largest area of the whole, and when the wind speed is less than 8 meters per second and the measurement noise is less than 30%, the generalized NDE in this region is equal to or less than 1 meter, which can demonstrate the overall performance of the SVM method. Nevertheless, the SVM method still suffers from accuracy reduction under large wind and measurement noise conditions, and the generalized NDE could go as high as 4 meters in region 4. The average deviations of hydrodynamic coefficients of each region are calculated, and their comparisons in sway motion are presented in Table 1, along with the benchmark value obtained from PNN test. Even though over half of the hydrodynamic coefficients maintain a good resolution, the others are affected by the wind disturbance to some different extents. The deviations of certain hydrodynamic coefficients increase from region 1 to region 4, such as Y prime VV, Y prime VU, Y prime RU, Y prime DDD, Y prime VVD, Y prime U. Besides, it can also be noticed that Y prime VDD, Y prime U, and Y prime UU are highly sensitive to the wind disturbance in the identification. And the reason might be that their values are relatively small compared with other hydrodynamic coefficients, which makes them more prone to be drifted. And then we show the results of validation using trajectory comparison. The validation is performed in the 3 different maneuvers under calm water conditions. Minus 25-degree turning, 25-degree zigzag, and random test, using 4 selected cases from each region as provided in the table. The model performance in the zigzag test can be regarded as promising, even though there are some small differences, and the Euclidean distance are less than 1.2 meter in this operation. What's more, from figure 6, it can be seen that the validation trajectory can follow the original one in a close manner. But when it comes to turning and random tests, the differences become more significant, especially for region 4 with the Euclidean distance over 5 meters. Figure 5 shows clearly that the turning circle becomes larger compared with the original one, while the figure 6 shows that the random test deviates from the expected position as time moves on, and the shape of the trajectory slightly deforms compared with the original one. And last, we come to the conclusion that the SVM method has good generalization performance, and the identified hydrodynamic coefficients agree well with the benchmark values, but some of them are significantly affected by wind disturbances, which results in large deviations from the true values. Simulation results show the effectiveness of the method in the cases where the wind speed is lower than 8 meters per second and the noise level is lower than 30%. And here are the references of this presentation. So that's all for the whole presentation. Thank you.